All right, so we're going to explain the partial sum of a geometric sequence and why it works. And let's use the sequence that goes 10 plus series rather 10, 20, 40, 80, and so on, all the way out to the last term. And the last term is going to be uh, 10 times 2 because the ratio is 2 n minus 1. You want a quick way to add up all of those things, except I'm not going to tell you where to stop counting. I'm going to leave n as a variable that could change depending on the problem. And so the quick way to do this is with the formula, and this is the derivation of the formula. So I want you to consider, since these numbers are multiplied by 2, if we multiply both sides by r, then we get r, which is 2. So I'm going to kind of go back and forth in between numbers and representation of numbers. And then the 10 would turn into 20, the 20 would turn into 40, 40, 80, and so on, all the way up until the last term. If you multiply this by 2, it would be so 10 times 2n minus 1 times another 2. This is 2 to the first. These two, the exponents add together. And so the last term would then look like 2 to the n. So let's take a moment here and notice, well, what happened was the 10 disappeared from the problem. That we can say, well, we lost u1, but the rest of it is the same. We still have all these pieces. They're going to be, we don't have, this is a new piece. All of these pieces are going to be represented here. 20, the 40, the 80, even this term, it's going to come right before this one. That 10 times 2 to the n minus 1 precedes 10 times 2 to the n. And that is Sn. So those are all those numbers are Sn, but without 10, which was the first number. So we have the total sum without the first number, but we also have gained an extra term. We've gained this u1 times r to the n term. So if we multiply by that ratio, we get kind of a strange assortment of variables. And if we combine our like terms, I know I left a big gap here, but Sn, this Sn is being multiplied, but this one's not. Let's combine some like terms, get them on the same side using subtraction. And over here, I don't like the leading coefficient to be negative, so I'm going to rephrase this as u1 times r to the n minus u1. Okay, so at least we got the terms on the same side together. And now the next step is to factor. Noticing here on the right-hand side, both of these terms have a greatest common factor of u1. So let's factor that out. Essentially undistribute a u1, and the remaining amount from the first term is rn. Like if you divide out a u1. If you divide a u1 here, it would be minus 1. Similarly, on the other side, the greatest common factor is Sn, and we can divide out an Sn, and the remainder is r minus 1. Okay, so taking a step further, if we divide both sides by r minus 1, we get the formula as we see it and have come to know it. So this formula is formula for adding up the first n terms, and it's left sort of uncalculated, so you can plug in how many terms you want to add and make that computation quite quickly. Now there's an alternate version. If you multiply the top and the bottom by -1, this r, so say for example we do the bottom first, the r would become negative and the 1 would become positive. Otherwise, 1 minus r. in the top here, let's distribute this 1 into this parenthesis, and the 1 would then be -1 times -1 is +1, and -1 times r to the n is -r to the n. Okay, and then u1 is going to stay there. So we have an alternate, and it's a preference which one you use. If you like your numbers to stay a certain way, you use one versus the other. But they do both accomplish the same thing. They add up the number of terms in a sequence up to a certain point.